Once again, I welcome you all. As a quick recap, in the last lecture, that is lecture 1 of week 1 of the course, we started our discussion with the different types of signals, analog, discrete and digital signals, and the advantages of a digital system over an analog system. From there, we moved on to the topic, that is the different types of number system and their conversion from one to another, starting with the conversion from decimal to binary number system and vice versa, followed by conversion from decimal to octal and back from octal to decimal conversion. Today, we begin our lecture section with the octal to binary conversion. The octal to binary conversion can be done by remembering the following octal to equivalent binary conversion table. As seen from the table, you can see each column, each digit of the octal number system is represented by a 3-bit binary number. On the left side of the table gives the octal number representation starting with octal number 0 to octal number 7, and the right column indicates the equivalent binary number. And you can see that each octal number is given as a 3-bit equivalent binary number. For example, the octal number 1 is represented as 001 in binary number. Similarly, the octal number 7 is represented in 3-bit binary number, that is 111. For example, we have to convert an octal number given as 500.734 to binary number. So, how to start with? Represent each octal digit to the corresponding 3-bit binary format, starting from the rightmost octal digit for the integer part of the octal number. So, my integer part is 500. So, I will start with the rightmost octal number, that is 0, then the next 0 and then 5. So, you can see that my 0, that is my rightmost bit in the integer part, is represented by the equivalent binary number, that is 000. Then the next 0 again by 3 binary bit numbers, that is 000, and then the octal number 5 is represented as 101. Similarly, for the fractional part, what we have to do, represent each octal digit to the corresponding 3-bit binary format, starting from the leftmost octal digit for the fractional part of the octal number. That means, after my fractional point, my leftmost octal digit, that is 7, I will start with 7, replace with its 3-bit equivalent binary number, that is 111, then followed by 3, I replace by its 3-bit binary number, that is 011, and then 4, which will be replaced by the 3-bit binary number, that is 100. So, what we get the equivalent binary representation for the octal number 500.734. Now, we will go from binary to octal conversion. So, we have, for example, we are given a number, a binary number 11101.1001, then again 11001. How to do the conversion from binary to octal? So, starting at the binary point, the binary bits to the left of the binary point are divided into group of 3 bits. So, the left of the binary point, starting with 1, you club 3 bits, that is 1000, then again you club another 3 bits, that is 010, and lastly we have got 3 more bits, 111. So, if you see that you have clubbed the first 3 bits 001, so that number is 1 in octal system, and then we have got 010, that is the octal number 2, and the last is 111, that is the octal number 7. Similarly, the fractional part of the binary number system, how to convert into octal. Starting at the binary point, the binary bits to the right of the binary point are divided into group of 3 bits. So, you can see that 100, that is after the binary point, that is the fractional part, 100, which indicates 4, then we have got 111, which indicates 7, and then 001, which indicates the octal number 1. So, what is the octal conversion now? 721.471. Now we go for the hexadecimal to binary conversion. The hexadecimal to binary conversion can be done by remembering the following hexadecimal to equivalent binary conversion. Instead of grouping of 3 bits as we are done from binary to octal conversion, here the grouping of 4 bits will be done. We have got the table here. We have got 4 columns. In column number 1, we have got the hexadecimal number, and in column number 2, the corresponding 4-bit binary number. Column 3, we have got the hexadecimal number starting from hexadecimal number 8 to the hexadecimal in alphabet form, that is F, which stands for the decimal number 15, and the equivalent binary number on the 4th column. Again, here we will go with an example. Convert B8.7F, which is in hexadecimal number system, to binary number. So, how to go about it? Represent each hexadecimal digit to their corresponding 4-bit binary format, starting from the rightmost hexadecimal digit for the integer part of the hexadecimal number. So, my rightmost digit of the integer part of the hexadecimal number system is 8. So, I will convert it to an equivalent 4-bit. What it will be? 1000, and similarly the hexadecimal number B, I will convert it into the 4-bit binary number, which corresponds to 1011. And after that, we will go for the fractional part of the hexadecimal number system. So, what we will do? Represent each hexadecimal digit to the corresponding 4-bit binary format, starting from the leftmost octal digit for the fractional part of the hexadecimal number. So, the leftmost hexadecimal digit of the fractional part is starting with 7. So, we will convert it into the 4-bit binary number, that is 0111. Then we have got F, we will convert again to the 4-bit binary number, which stands for 1111. So, now we have got the binary conversion of the hexadecimal number system, that is 101100.0111111. So, this is the equivalent binary number representation of the hexadecimal number, that is B8.7F. Now, what we will do? We have converted hexadecimal to binary. Now, we will convert binary to hexadecimal conversion. So, we have got an example over here. Convert 1100000110001110 to the hexadecimal number. Starting at the binary point, the binary bits to the left of the binary point are divided into group of 4 bits, that is the integer part of the binary number. So, we will group it into 4 bits. So, in the group of 4 bits is known as nibble. What we will do? We will start grouping the 4 bits. So, 1 to the left of it 000. So, that will be your number 1, and followed by 1101. Okay. So, that will give you the representation in hexadecimal, and after the binary point we have got 1000. Okay. And then what is 1000? That is the hexadecimal number 8, and then we group into 4 bits, then 1110, that is the hexadecimal in the hexadecimal number system that corresponds to the alphabet E, or the decimal number it is 40. Now, we will start doing some review questions. The first question is, the voltage and current signals which can take infinite values within a given range are known as, there are 4 options. The first is the discrete signal, the second option is the digital signal, the third is an analog signal, and the fourth is mixed signal. So, what will be the right answer? The right answer will be the analog signal. In the last lecture, we have discussed about analog signals. So, again I am repeating it up. What are analog signals? Analog signals are continuous time varying signal where the signal vary within a fixed limit or range. Okay. In the last lecture, we have seen the figure of the analog signal as xt, where x for an electrical or an electronic engineer can be either a voltage or current signal. We can see that at every instant of time, the value of signal changes. Then second question, the circuit in which the voltage levels can assume only a finite number of distinct values are called. There are again 4 options. The first option, it's a digital circuit. The second option, is it an analog circuit? Third option, is it a discrete circuit? And the fourth option, whether it is a pulse circuit. And the right answer is the first option, that is the digital circuit. In digital circuits, we use the digital signals, and digital signals are those signals whose amplitude takes a finite set of possible values. The digital signals carry binary data, that is 0 or 1 in form of bits. It can contain only one value at a period of time. So, you can come to the figure of the digital signal. So, again we can see that the amplitude Vt is divided into 4 levels, starting with level L0, then L1, L2, L3 and L4. Suppose the maximum value of my signal is 5 volt. So, there are 4 levels. So, each level will be of 1.25 volt. So, my L0 is 0 volt, my level 1 is between 0 to 1.25 volt, level 2 is between 1.25 to 2.5 volt, L3 is between 2.5 to 3.75 volt and L4 is 3.75 to 5 volt. So, if I take at the instant time t1, you can see that it is at level 1, that is no, it is at level 2, that is between 1.25 to 2.50 volt. Then the question arises whether I take the voltage at the instant t1 as 2.50 or 1.25. So, it is up to the designer to choose which value he has to go for. As a engineer or as a digital system designer, I will go for the lower value, that is 1.25 volt. Similarly, at time instant t3, you can see that it is at level 4, that is between 3.75 to 5 volt, but seeing the voltage at time instant t3, I will choose it as 5 volt. Similarly, at instant t5, you can see that it is at level L2, that is between 1.25 volt to 2.5 volt. So, I will choose its value as it is more near to the 2.5 volt, I will choose it as 2.50 volt. The next question is, the most significant bit of a binary number has a weight of 256. The binary number consists of how many bits? Again, there are 4 options. Option A is 9 bits, option B is 7 bits, option C is 8 bits and option D is 10 bits. Let us take an example. Suppose my number of bits is 8. So, how many decimal numbers I can represent? I can represent decimal number 0 to the decimal number 255, or for representing the maximum bit of a binary number has a weight of 256, then I should have 9 bits. So, my right option is option A, that is 9 bits. Or you can say that for an n bit number, the decimal number we can represent is from 0 to 2 raised to n, where n stands for the number of bits minus 1. So, here we can have, what is n here? The n here is 9 bits I have taken, so 2 raised to 9, that is how much it comes? 2 raised to 9, it comes to 512 minus 1, that is 511. I can represent any decimal number from 0 to the decimal number 511. The conversion of a hexadecimal number to a binary number can be easily done by replacing each hexadecimal number by its corresponding. There are 4 options again. The first option is a 3-bit binary number, the second option is a 4-bit binary number, the third option is a 2-bit binary number, and the last option is a 8-bit binary number. So when we have gone for the conversion, we have seen that we group 4 bits from hexadecimal number to a binary number. How we do the conversion? We group 4 bits, and this 4 bits is known as a nibble. And therefore, the correct option in this question is the second option, that is the 4-bit binary number. The next question, the weights assigned to the least significant bit and the most significant bit of a 6-bit binary number is. So, how the weights are assigned? It starts with the least significant bit, whose weight is 2 raised to 0, and it goes up to the most significant bit, whose weight is 2 raised to n minus 1. So, we have got a 6-bit number. So, therefore, its least significant bit carries a weight 2 raised to 0. That means, the weight of the least significant bit is 1, and the weight of the most significant bit is 2 raised to n minus 1. That means, n is 6 minus 1, that is 5, and 2 raised to 5 is 32. Therefore, the weights of the least significant bit is 0, and of the most significant bit the weight is 32. Therefore, the last option, that is D. The conversion of octal to hexadecimal number system and vice versa is similar in which type of number system? We have got 4 options. The first is the decimal number system, then the binary number system, then the hexadecimal number system, and the last option is the octal number system. So, any conversion, whether it is from decimal to binary, binary to octal, octal to hexadecimal, or octal to binary, the best or the simpler method is to go for the binary number system, that is option number B. These are some of the practice problems. I have given you 5 questions. You practice it at home, and in the next lecture we will discuss about it. Now, we will go to the next topic, that is binary arithmetic. Arithmetic operations in digital systems are usually done in binary because of easy design of logic circuits to perform binary arithmetic. Arithmetic operation in binary number system is carried out in much the same manner as we do in decimal number system. So, we will start with the binary addition. There is a table shown. For addition, we have got 0 plus 0, that is equal to 0, then 0 plus 1, that is equal to 1, then we have got 1 plus 0, that is again equal to 1, and then we have got 1 plus 1 equals to 0, that is the sum part, and we have got a carry forward, that is the carry bit 1. Then we go for the binary subtraction. You can see the subtraction table. 0 minus 0 is 0, 0 minus 1, we can see that the minute value is less than the subtract value. The minute value is bit 0 and the subtract value is 1. So, therefore, you have to take a borrow from the next more significant bit. So, you take a borrow, then it becomes 1 0, that is 2, 2 minus 1 is 1, okay. And then you got 1 minus 0, that is equal to 1, and 1 minus 1, that is equal to 0. Now, we go for an example. You have got 2 binary numbers 1001.011 and you have to add it up with 111.010. So, we will start with the fractional part, that is 1 plus 0 1, then 1 plus 1, the sum is 0, then you carry over the 1, that is the carry forward. You have got 1 plus 0, that is 1, then 1 plus 0, again 1. Then the binary point comes, then you have got 1 1 in the integer part, you add 1 plus 1, that is sum is 0 and the carry is 1. The carry forward goes to the next bit. So, you have got 1 plus 0 1, then 1 plus 1 again 0, and then you have got again a carry forward which goes to the next significant bit. So, that is again 1 plus 0 1, 1 plus 1 0, again we have got a carry which goes to the fourth bit, that is the most significant bit in the, and you add that 1 plus 1 0, then you have got a carry 1. Therefore, the final answer will be 10000.101. Now, we will go for similarly the subtraction of two binary numbers. We have got the subtract 1 1 in binary number system and the manual, that is 1 0 0 0. You have got 1 3 times 0. So, you have to subtract it. You see that the least significant bit, the manual 0 and the subtract is 1. So, you have to borrow a 1 from the next significant bit. Again you can see that it is a 0. So, then you go to the next significant bit in the manual, again it is a 0, and then you go to the next significant bit, again it is a 0. Then you have got the most significant bit which carries a bit value 1. So, you borrow that 1. So, it comes to the next significant bit, it becomes 1 0. You borrow 1 from that. So, again it goes to the next significant bit, it becomes 1 0, and again you borrow 1 from here, it goes to the next significant bit, it becomes 1 0, and again you borrow is 1 from this and it goes to the least significant bit, becomes 1 0. That means 1 0 minus 1 you get as, that is 2 minus 1 1. Now, as you have borrowed, the remaining bit will be 1, therefore 1 minus 1 is 0. Similarly, in the third you have borrowed already 1, so 1 minus 0 1. Similarly, in the third bit you can already borrowed 1, therefore 1 minus 0 1, and from the most significant bit of the manual you have already borrowed that most significant one, therefore that is remaining as 0. So, 0 minus 0 will be 0. So, you have left with the value 0 1 1 0 1. Borrowing 1 from a column is equivalent to subtracting 1 from that column. Now, we come to the multiplication of the binary number system. 0 into 0 is 0, 0 into 1 is equal to 0, 1 into 0 is equal to 0, 1 into 1 is equal to 1. So, we are given two numbers for multiplication. The same way as we do in decimal number system, we multiply and you can see the answer here. So, you started with 1, multiplied 1 1 0 1, then you have got 1, again you move towards one significant bit towards the left side. So, you have got 1 1 0 1, then you multiply it by 0, you will get all the 4 zeros, and the last is 1, you again multiply, you get it as 1 1 0 1. You add it up and you will get the final answer as 1 3 times 0, then 1 1 1. Similarly, in binary division, we have given an example how you go for the binary division. The dividend is 110.101 and the divisor is 101. So, that is the decimal number 53.75. You are dividing it by the decimal number 5. So, you should get an answer equals to 10.75. So, you can see the quotient, and you can, from that you can match it up the values, fine. I will go to the next topic, that is the complement. Complements are used in digital system for simplifying the subtraction operations, as the digital system need only one common hardware circuit to handle both types of arithmetic, that is the addition and the subtraction. That is the beauty of the complements. There are two types of complement for each number system with base B or radix R. So, for a decimal number system, we have got the tens complement and the nines complement. The first is referred as B's or R's complement and the second as B minus 1 or R minus 1's complement. That is for decimal number system, as I already told. If it is B's complement, that is the tens complement, and B minus 1's complement will be the nines complement. Similarly, for a binary system, it will be the 2's complement or the 1's complement, or for an octal number system, it will be the 8's complement or the 7's complement. In digital system, as arithmetic operation is performed in binary, the discussion now will be on binary complements. So, as I told you, there are two complements, that is the b's complement represented as 2's complement and the b minus 1's complement, because in a binary number system the base is 2 minus 1, and we call it as the 1's complement system. In a binary number system, the value of base is 2, and when it is substituted in the name, the two types of complement, as I told you, the 2's complement and the 1's complement, that is the b minus 1's complement. So, let us start with the 1's complement. I have to find the 1's complement of a number, of a binary number n. How it is obtained? It is obtained as 2 raised to n, that is a small n, minus 1 minus the capital N, where the small n indicates the number of binary bits. Therefore, the 1's complement of a number, I can write it as, that is I given as n with asterisk, that is equal to 2 raised to n, where n stands for the number of binary bits, minus 1 minus n, where n is the binary number whose 1's complement we have to take. So, we will go for an example. Find the 1's complement of 1001, that is the binary number 1001. So, how many bits this binary number has got? It has got 4 bits. So, 2 raised to 4, that is the decimal number 16. So, how you will represent the decimal number 16 in binary? It is 1 with the 0 0 0 0 you have got, and then you subtract 1 from it, that is 16 minus 1, that is 15, and in binary representation it is represented as 1 1 1 1. Now, you have got 2 raised to n minus 1. What is its binary value? That is the decimal number 15, that is 1 1 1 1 minus the number whose 1's complement we have to take, that is 1 0 0 1. So, we have subtracted it, and you can see that the result is 0 1 1 0. The other simple way to take the 1's complement of a number is just to complement each bit of the given binary number. That means, if the bit is 0, you complement it, it will become 1, and if the bit is 1, you complement it and it will become 0. Now, you go for the 2's complement. The 2's complement of a number n is obtained by 2 raised to n minus n, where 2 raised to n stands for the number of binary bits minus n. So, therefore, we can say that the 2's complement of a number denoted as n with asterisk, that is equal to 2 raised to n, the small n, minus n, the capital N, whose 2's complement we have to take. We will go for an example. Find the 2's complement of 1001, that is the binary number. So, as you know that this number has got 4 bits. So, 2 raised to n, that is equal to 16. In binary form, we can represent it as by 1 with 4 zeros. The 2's complement of that number, that is 1 with 4 zeros minus 1001, you subtract it and you will get the value as 0 1 1 1. So, this is one way of doing the 2's complement of any binary number. The second simple way is like that. You take the 1's complement of that number and then add the binary number 1 to the least significant bit of the result. So, we know that we will go for an example. Find the 2's complement of 1001. So, first we will take the 1's complement of this number. So, starting with the leftmost significant bit, the leftmost significant bit is 1. So, its complement will be 0. Then we have got 0, it will be 1. Again we have got 0, it will be 1, and the most significant bit is 1. When we complement it, it becomes 0. Now, we add the binary number 1 to the least significant bit of the 1's complement, which we are right now obtained. So, it will be 0 1 1 0 plus 1 we are adding it to the least significant bit, the answer will be 0, 1, 1, 1. So, this will be the 2's complement of the number. You can see the addition has been done, you are getting the result 0, 1, 1, 1. Subtraction with complement. In a b base number system, that is with the base as b or the radix as r, the subtraction of two unsigned numbers x minus 1 y is done as follows. We have got two numbers, binary numbers, where x is the your minute and y is the subtrahend. So, how you go about it? So, we will start with the b's complement, that is the 2's complement. We are making an assumption here, that is my minute is greater than or equal to my subtrahend, that is y, that is x is greater than or equal to y, that is x minus y. So, how we go about the subtraction use with 2's complement? So, first take the 2's complement of the subtrahend. You know that the 2's complement of the subtrahend, that is y with asterisk, is equal to 2 raised to n, where n stands for the number of bits of the subtrahend minus the number or the subtrahend y. Second, add the minute x with y. So, when we add it, what you get, x plus 2 raised to n minus 1, or you can rewrite it as 2 raised to n plus x minus y. Why? Because we have already made an assumption my x is greater than y. So, when you add it, the sum will produce an n carry, discard this n carry, and the remaining result is x minus y. Now, we go over the second assumption, where the minute x is less than or equal to y, that is the y is the subtrahend, s is less than equal to y. What we have done before, again we take the b's complement of the subtrahend and it is obtained as y asterisk is equal to 2 raised to n minus y, and then second add the minute x with the y star or y asterisk, or you can get it as 2 raised to n minus, you can write it as 2 raised to n minus within single bracket y minus x. The result will not produce an n carry, because if you see that 2 raised to n minus y minus x, what it shows, you are taking the 2's complement of y minus x. So, that means the result is negative, and again take the 2's complement of the result. Okay. Now, we will go for the 1's complement, that is the b minus 1's complement. Again we will start with the same assumption as we have done for the 2's complement. X minute is greater than or equal to y, that is a subtrahend, x greater than or equal to y. First take the b minus 1's complement of the subtrahend, y is obtained as, find 2 raised to n minus 1 minus y, where n is the number of binary bits. So, you can write that y star is equal to 2 raised to n minus 1 minus y. Second, add the minute with the y star, or you can write it as 2 raised to n minus 1 plus x minus y. So, the sum will produce an n carry, and this carry is known as the n around carry, and add this n around carry to the least significant bit of the result to obtain the final result. Now, we will go for the second assumption, your x, that is the minute, is less than or equal to y, that is the subtrahend, x less than or equal to y. Again we will take the b's minus 1's complement of the subtrahend y, and it is obtained as 2 raised to n minus 1 minus y. Fine. So, you can write that y star is equal to 2 raised to n minus 1 minus y. Second, add the minute x with y. You can rewrite it as 2 raised to n minus 1 within the brackets minus within the bracket y minus x. So, again you can see that it is the 1's complement of the number y minus x. So, the result will not produce an n carry, the result is negative, and again take the b minus 1's complement or the 1's complement of the result. Hope you had a good learning experience watching this video. Thank you and see you all in the next lecture. Until then, practice the problems given as practice 1. We will be solving some of the questions of it in our next lecture. Thank you.